Thanks for joining me. I'd like to give you a tour of a very different and exciting Excel model we've developed to analyze performance data, but it's so much more than just another spreadsheet file to crunch trend data. Our models can store and quickly analyze millions of data points, many millions in fact. They can compare actual operating results with baseline and design data and quantify to what level the performance objectives have been met. And the interactive dashboards we develop allow users to explore the data and analysis in a straightforward and intuitive way. Data models we create are developed using Microsoft Excel and its business intelligence add-ins Power Query and Power Pivot. However, you don't need these add-ins to view and explore the data model. The new tools available to us, and some old tools we use in new ways, allow us to design better ways to analyze performance data that produce higher quality insights for everyone involved. So what do we mean by better? Less costly, more timely, greater value. Let's look at the three things that have to be done after the data has been collected from the site. We have processing, analyzing, and reporting. Processing. This phase includes all the activities to organize, select, combine, and clean up raw data files prior to doing any analysis. This step can be very time-consuming and require a lot of manual work. Processing data can be so demanding in large part due to all the different ways in which field data can be received. It can range from one sheet and one file with just the data you need, and this is rare, or 12 monthly folders with 3 files in each month's folder, and each file has between 3 and 5 sheets, with each sheet containing a block of buildings and a range of dates. Point names listed in the first row of each sheet may stretch across 100 columns or more. And if the source file is not Excel, there are other steps that must first be taken. The analyst's job here, for example, is to find all the data for 10 specific zone temps in 5 different buildings from the roughly 140 tables of raw data and from among the nearly 15,000 different point ranges. And you're trying to find a point named something like Building 4 AHU1 Admin Zone Temp, but the actual point name looks like. We now have powerful query functions integrated with Excel that expedite us getting the right data into the right format. From the data model, we can poke into files, inspect and select what trend points we want from source files in nearly any format we'd encounter without intermediate steps to convert to Excel first. We can combine and merge data from multiple files, and we can shape the tables for most efficient data storage and use before importing into the model. Analyzing. The details of this process are highly dependent on the systems and type of verification that is required. It could be as straightforward as determining the total run hours for a particular fan unit over a 3-month period, or it can involve a chiller plant where calculations use a dozen or more trended parameters and the results are aggregated to create actual load and efficiency profiles. Many times with trend analysis, you end up with custom-made one-off files that can be large, complex, and a little difficult to follow at times. One reason is pivot tables. Standard pivot tables are very efficient at making sense out of large sets of data. However, all of the fields for that pivot must reside in the same Excel table. This means that you're adding complicated lookup and index match functions to consolidate data from other sheets or files into one table for the pivot table to use. The frequency of the trend observations can influence the design and speed of the analysis too. Many times there's a mix of trend intervals within the same project, 15-minute, 45-minute, hourly trends captured on the 18th minute, and change of value type trends that may log an observation every several hours or even days. Then, after it's determined from the trend data what the systems were actually doing, comparisons to the proposed conditions must be made. Let's say it's determined from the trend data that a motor ran 5,000 hours for the year. Its design run hours were 4,000. You know that it didn't achieve 100% of the savings target, but were any savings achieved? That depends on what the baseline run hours were. The actual performance needs to be evaluated in relation to both the baseline and design data. Trend analysis files can contain a number of worksheets, links between them and external files, and users can find it difficult to trace through from the highest level results down to the individual system performance without getting disconnected. Some files are expertly created and many times are unappreciated for the level of effort that went into them. If they're wrong, they're overvalued no matter what it cost. We now have related tables. It is one of the key features of the software behind the data model. Tables loaded into our model can be from separate sheets, files from files of different formats, and they can be combinations of many different files, such as monthly trend data that is merged using our query routines. Relationships are then established between certain tables, and once the proper relationships are in place, we have a lot of analytical horsepower ready to put to work. We can overcome a few common obstacles a lot quicker with related tables. We can perform calculations across related tables with functions that require less memory and execute faster than traditional lookup and similar functions. We can reconcile long system trend point names with common, more friendly ones. And the troubles caused by odd trend intervals are met much more effectively. This ties in with the data processing efforts. In general, we want to conform the data to match the analysis method, not the other way around. The pivot tables in our model have been supercharged too. Conventional standard pivot tables can only accept data that is in the same source table. We can now pivot any field from any of the related tables in our model. We can also perform calculations on the pivot table results. And we have pivot table filters that can be graphically arranged around the tables and charts to make them easier to use. These new pivot tables give us the power to make the sometimes difficult comparisons between actual results and the baseline and design data, each of which may have its own granularity. Trends may be every 30 minutes, design data may be a matrix of 4 points representing a reset strategy, for example, and the baseline may be a bin table of outside air and hot water supply temperatures. These differences can make comparisons more challenging and time-consuming than they first seem. Reporting. It often takes longer than expected to take a good analysis and parse out the pieces you want and need to share with your customer. You don't necessarily want to or can turn over complete working files, and preparing separate customer versions is time-consuming. With our new data model, communicating the key aspects of the analysis and conclusions is streamlined. Tables and graphs are dynamically updated based on user selections and can be readily copied into report documents or further customized. There is no need for a separate major effort to generate these items for your report. Both periodic and annual reporting can be consistently and reliably done. Another way to be better is to be more timely. Like money, there is a time value to information. A lot of spreadsheet files designed to perform trend analysis require the same level of effort every time data is updated. Each time it's like a brand new analysis. For this reason, periodic trend reviews are not always done when or how they should be. Using our new data model, we can help compress the time required to transform raw data into something worth discussing with your customer. First, the trend data tables in the model can be connected to the source files, so when new data is added to the source, the model is refreshed and only the new data is imported. Or, for entirely new files, our queries can be amended to do the same thing with this batch of files as was done with the last. And new files can be imported into our model and relationships established with the other tables. The calculations, tables, and graphs will all work with the new data. Being more timely with useful insight should mean better quality interactions with your customer. One way value is added to something is to increase its utility, to make it more useful in more ways to more people. The data model we create is a triple duty file. All of the data is contained in our model, all of it. The trend data that's imported, the baseline and design tables. This provides a file with better transparency and better compliance with contract regulations and organizational standards. Also in the file are all of the calculations for the analysis, including calculated columns that are added to imported data tables and calculated fields that drive and utilize pivot table results. Dashboard design concepts give our model broad appeal. The technical pro can move from the highest level summary table through to the back end and see the imported source data. A less experienced user can step through the data and graphical summaries without trouble or confusion. and it's easy to share the model on a network, in the cloud, on CD or email, or all of the tables and graphs can be printed out individually. What makes for a higher quality insight? They are relevant, not just timely, but connected to the big picture. Telling your customer you see from the trends a problem developed 2 months ago is better than saying it was 10 months ago. They are specific and help identify the cause or causes of any performance deficiencies. And they quantify in a meaningful way. Ratios and percentages are good, but dollars and energy units can be better at communicating the real, tangible impact of performance shortcomings and improvements. What insights can be gathered from our dashboard? In our example, we have 7 buildings and a total of 25 zones with independent schedules and set points. Each zone has been equipped with programmable scheduling and zone temperature control strategies. The by building summary in the upper left section includes information on the proposed and actual savings. The last 3 columns show us to what degree the performance goals were met for the 2 strategies and overall. Our eyes are drawn to the red flags here, and we can see that overall, Building 1330 is our worst performing building. From the chart to the right, we see that this building doesn't contribute a lot to the total savings, but the savings loss is about 1/3 of the total negative variance for the project. So let's take a closer look into Building 1330 and see what's contributing to the poor performance of these 2 strategies. There are 2 systems in this building. One is operating just as we'd expect, and the other one is not. And we can see the programmable scheduling piece is not hitting its target, but the zone temperature control strategy is really off the mark. This chart in the bottom left graphs the average daily run hours by typical weekday and weekend period. And the extra operating hours during a typical weekday is noticeable here, but during the weekend periods it's much more pronounced. And the chart in the bottom right plots the 4 components of the zone temperature control strategy. We have occupied and unoccupied for both heating and cooling season, and we can see here for the first floor AHU1 unit that we achieved the least of our temperature control goals during the occupied cooling period. So let's keep drilling down and we'll examine some 24-hour profile data. Here we have a graph of typical 24-hour operation based on what we've selected above. In this view, we're looking at a typical weekday profile during the heating season, and since everything else is selected up here, this graph is an aggregate profile of fan status in the columns and zone temperatures in the lines for all the buildings and systems that we have in our project. The data table below the chart gives us some more information. We have the baseline design and actual fan status of each hour are indicated with the circle icons, and the actual hourly zone temperature values are also displayed. Let's examine that unit in Building 1330 that we saw was not performing well. And we can quickly see the extra runtime here that was not planned at the end of the day. The temperature control generally looks good up until that time. So what about the weekend? Again, we're still in the heating season, and things are starting to look a little strange here. There is more actual runtime than was designed during the daytime period. And the second item we'll notice is that how the actual zone temperature, while looking good during the unoccupied period, starts approaching the baseline temperature as soon as the fan starts running. The data table now includes some half-filled circles. Let's remember that we're looking at an average hourly profile for weekend days, and the half-filled circles for the design conditions may indicate that there were planned operating hours on Saturday but none on Sunday. So let's take a look into this weekend profile. And for Saturday, we can see that there were no planned hours for this day, and we can see this from a lack of the red design columns in the chart, as well as the circles in our data table. Now let's take a look at Sunday, and we see now that there were planned hours for Sunday. Let's look at the weekday profile during the cooling period, And here we can see there was a pretty narrow range during the occupied period for the zone temperatures, and we seem to be falling in between the baseline and design target. Let's look at the weekend. And from the graph, it looks like our actual zone temperature from morning to early evening is closer to the baseline than the design. We've already seen for this unit that there were no planned operating hours during Saturdays, but some on Sundays. So let's take a look at Sunday first. And except for that extra runtime at the end of the day, things generally look okay. Take a look at Saturday. And here it is clear that the zone and air handling unit are operating in the occupied mode for a part of the day when it was not designed to do so. And we can contrast this with the picture for the other unit in that building that was performing just as expected. And we can see here that there are no unplanned operating hours, and the actual zone temperature line is tracking very closely to the design set points for both occupied and unoccupied periods. And this is what we'd like to see for all units. So in a few minutes, we've isolated the poor performance for this building 1330 first floor AHU1 unit to unplanned Saturday operation and the zone temperature set point during occupied periods of the cooling season. We use Microsoft Excel and its business intelligence add-ins to create our data model. This model gives us the ability to create context for your data, but the trend data alone does not paint the full picture. Likewise, the baseline and design data by themselves are meaningless when it comes to evaluating performance. All three, baseline, design, and actual, need to be placed in context with each other to make sense of complex systems. From there, the achieved performance can be quantified and the best course of action determined. Contact us to discuss how our customizable data models can transform performance analysis for your current and future projects.